My name is Lori Ziegelmeier, and I'm a professor at McAllister College. And today I'd like to introduce a tool to measure dynamics of time-varying systems. So imagine that you have some data. For instance, here's examples of biological aggregations. So you can think of these as individual particles that have both position and velocity. So maybe these are schools of fish swarming around, or maybe they are a flock of geese flying in the sky, or possibly some insects nesting as well. And the idea is that we would like to understand the dynamics of these various time varying systems. Okay. We would like to do so with a topological lens. And so I want to give a very brief overview of one pipeline in topological data analysis, and then show how this is modified to incorporate time. So first, imagine we have some data, and perhaps this is position velocity data for a single snapshot in time. So we can envision this as a point cloud that we want to understand the topological structure of. Now, from these data, we want to build connections between our points to get a topological object called a simplicial complex. And once we have this topological object, then we can determine the structure by computing homology. Loosely, homology is a way to calculate the number of holes of various dimensions. And what we want to do is create these various connections through a different scale parameter. So for instance, if we have a smaller scale parameter, we might get a different simplicial complex and different homology than if we had, say, a larger scale parameter. So for instance, if we have our isolated points, we could consider making connections between these points whenever we have some epsilon ball that pairwise intersects. So this is something known as a Vietoris-Rips complex, where anytime we have k+1 points that pairwise intersect, we would form a k-simplex. So if we have 2 points that pairwise intersect, we would have an edge. If we have 3 points that pairwise intersect, we would have a filled-in triangle, and so on. Now, persistent homology can actually assess through these varying scales the topological structure, and it is represented in a topological barcode. So here we have a dimension 0 barcode, which counts the number of connected components at various scale parameters. So at a very small scale parameter, we have our points all isolated. Once connections are made, the features start to merge together, and these bars will actually die. So until we finally have all points connected into a single connected component. So dimension 0 measures connected components. Dimension 1 homology measures topological loops. Dimension 2 homology measures trapped volumes, and so on. So this is encoded in something called a Betti number, which measures the rank of the homology group at various scales. Now, what we will do is want to apply this pipeline to time varying data. So we're going to summarize these topological features in the following way. So in this range of values, we have 7 connected components. In this range of values, we have 6. In this, we have 3, 2, and 1, and so on. So this information here, we are going to take as a vector to represent the time, or to represent the topological structure at various scales. Now, I motivated this presentation by saying that we wanted to take this pipeline and add time into it. So the way we're going to do this is something called a Crocker plot. So essentially, a Crocker plot does that pipeline I just introduced, where we record for a fixed snapshot in time and a varying proximity parameter. We can think of this as a vector through this scale parameter. Then we can do this at all sorts of different times, and we can get a matrix to represent the Betty number as it varies through both proximity parameter and through time. Okay, so this matrix here now carries topological information across both scale and time. And we have come up with this sort of clumsy acronym calling this a Crocker plot, where we take this matrix and visualize it with a contour plot because we thought we were funny and clever to have a Crocker plot to display a Betty number. So I'll let you see if you catch that joke here. But in essence, this visualization is a means of displaying topological structure as time varies. Now, I want to mention that this is a very simple representation, and it is an approach that is not as sophisticated as several other approaches that are already out there. So this is, of course, not the only means to measure time varying data, but it's one approach. And in the rest of the presentation, I want to just give you a very high level overview of how you might be able to use these Crocker plots. So in this first slide, I want to show you how a Crocker plot can reveal dynamic behavior. So on the right over here, we have a very common model of a dynamical system representing point particles that interact with one another and produce aggregate behavior reminiscent of things like a school of fish swarming around. So as time goes on, we see we have these particles. Red represents moving counterclockwise, and blue represents moving clockwise. And as time goes on, we see that we have this structure where most of the particles move clockwise and a small minority move counterclockwise. So this is called a double mill structure. Now, before topology started being applied to this, the biological modeling community would analyze the dynamic structure with something called an order parameter. And an order parameter is just a tool from physics to come up with a time series of behavior at various times. So for instance, perhaps you might ask, are the particles all aligned or polarized? And that's what the red line does. Or do they have angular momentum? And that's what the blue line does. And there's something else called absolute angular momentum. Oh, I'm sorry. The green line is angular momentum, and the blue line is absolute angular momentum. And if we say if the particles are moving in a circle, then they would have high angular momentum. And the fact that there's a small minority moving counter to the majority of particles, we see that these two lines are not identical. So using this tool, we could assess that there is, in fact, a double mill structure. Now, these tools were defined using a priori knowledge of the data that was hoping to be analyzed. Now, let's restrict our attention to this Crocker plot. So this is a dimension 1, so measuring topological circle Crocker plot. Here I have not displayed the Betty, or the information for Betty numbers greater than 5, interpreting that as noise. Now, what we observe over here is that we have two topological loops for a period, okay, of both simulation time and proximity parameter. And then after we get to a larger scale, we only have one topological loop. And you can check out our paper to convince yourself that this does in fact relate to this double mill structure. Okay. Another way Crocker plots have been used is to do parameter identification. So again, using the Dorsonian model, the very common model in the previous example, we created a huge corpus of various simulations of different parameter sets. And what we wanted to do was to use this order parameter, so the things like polarization and angular momentum and so on, to come up with time series for each of the different simulations. Alternatively, we use topology-based description to come up with a representation of all of these different simulations. And we can think of these time series or Crocker plots as a feature vector that can then be fed into machine learning. Now, the topology approach is problem independent without using a priori knowledge, where the order parameters are problem dependent. And what we observed is that actually the topological approach yielded higher classification accuracy with regard to the various different parameter sets. In another approach, we wanted to use the Crocker plots to assess model validity. So in previous work, researchers created two models to represent some experimental data from PA aphids. And there was an interactive model that assumed that PA aphids interacted with their neighbors. And there was a control model saying that there should be no interaction between these PA aphids. And again, we did a comparison with order parameters and a topological approach. And what we observed is that order parameters with a priori knowledge, or really that are the basis of the interactive model, such as distance to nearest neighbor or percent moving, revealed the same structure or the same results, that the interactive model was more faithful to experiment than the control model was. And this was also found with the topological approach, which was not using a priori knowledge. Now, I want to just conclude and say that Crockers are not actually stable. So in topological data analysis, one of the reasons it's become so prevalent is that topological barcodes are stable with respect to the bottleneck metric. So what this means is if you have two data sets that are very similar, then their topological barcodes are also going to be similar. This is not at all true in any sense for these Crockers. However, we have introduced a new tool, a Crocker stack, which incorporates a rank invariant to get a stability property that's reminiscent of a stacked set of persistence diagrams. And this new tool is in fact stable. That said, I want to give a plug that Crockers are still useful. We have shown that they are useful for revealing dynamic structure, for doing parameter identification, and for doing model comparison. So that's it. If you would like to find more details about any of these approaches, all of these papers are posted on my website, and I also have code for the Crocker plots posted on my website as well. So thank you.